looking at the logistic model. So the logistic model says that if you have a population whose time, n of t, satisfies this logistic equation, that is dn dt, this net rate is equal to r times n. So you've got more people present, then n prime gets larger. And it's also not just depends on n, but on the room for the population to grow into. 1 minus n over k represents how much space there is in the environment for growth. K is what's called carrying capacity. And in this exploration, questions 1 and 2 ask you to determine how this dependence is on R and the dependence on K. So in question 1, you're going to fix your initial population size to be 25 and fix K to be 100, and then look at 8 different graphs that you get when you sweep R going from minus 0.5 to 2. You should then address these questions that are being asked here. How does this growth rate constant affect the long-term behavior of the population? So you want to look at the limit of n of t as t goes to infinity and see whether changing R affects that or not. And the second question is, how does it affect the dynamics of the system? What do we mean by the dynamics? We mean what happens, is our function increasing, is it decreasing, does it bend this way or bend that way, whatever. It's what the graph looks like. Is it, does R affect that? And draw your conclusions based on these 8 graphs that you get here. In question 2, you're going to now fix R and vary K. So you're going to set the initial condition 25, initial population size to be 25 and R equal to 1.2, and then sweep on different Ks from 70 to 150 and draw these solutions. And again, address exactly the same 2 questions. What's the limiting behavior as t goes to infinity? How does that depend on K? And how does the carrying capacity affect the dynamics of the system? So those are the questions that you're asked to address. You'll get 8 graphs from question 1, 8 graphs from question 2. In total, you'll have something like 16 graphs. And question 3 asks you to look at these graphs a little more carefully. What do we mean by a little more carefully? Let's look at what question 3 is asking us. It says that sometimes the rate of change of population size is increasing. It tells you sometimes n prime is increasing. If I tell you that a function is increasing, what can you tell me about the derivative of that function? Positive. The derivative has got to be positive. So if I tell you that n prime is increasing, you know that n double prime is positive. Now when you have a graph, and this is a function of t, and you know that the second derivative is positive, so over here, so here's an example, one of the solution curves. Here it's concave up, and then here it's concave down. There's a spot where the concavity changes. But let's see. If I tell you that n prime is increasing, that means when I take the second derivative, it's positive. One of the things that you learned from your Calc 2 days, you had this silly little diagram. Did you have this silly little diagram? Take the second derivative, and the second derivative is positive. That means that the graph is concave up. It holds water. If you take the second derivative, and the second derivative is negative, the graph is concave down. And it's all really because in this situation, n prime, if I look at the slopes, the slopes increase as I move in t. Here, n prime is decreasing because the slopes start out positive, go to 0, and become negative. As I vary t, curves. So that's all this is saying. So let's see. So let's go back to what this problem was saying. It says that sometimes n prime is increasing, and sometimes n prime is decreasing. N prime is decreasing, that means that the second derivative is negative, and the graph's got to be concave down. So he says, by looking at your graphs, the 16 graphs you have in problems 1 and 2, try to predict some relationship between r, k, and n that distinguishes between these two situations. The situations are being concave up or concave down. Use ODE Architect to test your prediction by graphing some more solution curves. And then finally, confirm this by doing an exact analysis of n double prime. Let's just go back, let's go look at what ODE Architect says. If you open up ODE Architect and go to your library, in the folder Population Models, there's a logistic equation for population growth. Here we have several graphs over here of n versus t. And here is one of these solution curves. And here it appears to have a fixed, all of these graphs have fixed k's, but it's like different initial conditions. The initial conditions are changing here. And if you look at this graph, it's concave up, and it's concave down. Here it's concave up to a certain point, and then certainly concave down near the top. The question is, what determines where the concavity changes? Well, in several of the labs, some of you have drawn a graph of n prime versus n, or in the case of the sardine population, you look at s prime versus s. And it's not clear what's happening here. Let's look at, if I look at the graph of n prime versus n, oh, here my n prime is increasing as n is increasing. So in these examples, n is certainly increasing. And as n increases, by the time it gets to 48, n prime stops increasing. It starts decreasing. If I look at n between 0 and 48, as t changes and my population size increases, the graph is concave up. When I reach 48, my n prime stops increasing and starts decreasing, and my graph is concave down. That's the import of this n prime versus n graph. It tells you how the graph of n, or at least it tells you where n prime is increasing and where it's decreasing, and therefore you know where the graph is concave up and where it's concave down. Now we don't quite know what the relationship is between 48 and k and r. Maybe there's some relationship here. That you'll have to try to figure out yourself. But this graph here, that's really the reason why we have that interest in these two. So that's what ODE Architect can tell us. There are several graphs over here. See how your predictions fit into these. But the main thing is you need to do an exact logical analysis. This last statement here. Confirm, it's not just try. I want you to confirm your prediction by doing an exact analysis of the second derivative. What do we mean by an exact analysis of the second derivative? Well, if I look at my differential equation, n prime equals r times n times 1 minus n over k. In order to understand where the graph is concave up or down, I need to know where n double prime is positive and negative. So my first task is to figure out what n double prime is, and I need to figure it out in terms of r, n, and k, because that's what this problem is asking for. Try to predict the behavior of this concavity based on r, n, and k. If I differentiate this expression with respect to t, not differentiating with respect to n, the derivative of n prime with respect to t is n double prime. Prime is just with derivative with respect to t. And if I use my product rule, this is a function of t, this is a function of t, it's going to be r times the derivative of the first function, n prime, times 1 minus n over k, plus rn times the derivative of 1 minus n over k. The derivative of this with respect to t is minus n prime over k. Now here I've got this n prime instead of n. Well, I have an expression for n prime in terms of r, n, and k. Simply substitute that expression for n prime. And then you'll have a long expression in r, n, and k, and you should then try to figure out when n double prime is going to be positive and negative based on that expression in r, n, and k. Once you've done that, okay, you'll get some sort of thing like, oh, as soon as n is bigger than 48, the concavity changes. If I look over here, oh, the concavity does change at 48, not just for this graph, which appears to be what's over here, but even for these other graphs, the concavity seems to change at 48. And try to verify whatever your prediction is based on this exact analysis, that in fact that's what happens at the 16 graphs that you had in problems 1 and 2. So that's it. See you this afternoon. You can start working on the lab now if you want. Or